Okay, well, I'd like to thank the Programme Committee for inviting me. I feel very honoured to speak here today. What I'd like to tell you about is what I'm doing in my second job. As you can see, I'm working at Chalmers University, as I have done for many years, but I'm also spending half my time at a little company called QuickCheck, of which I'm the CEO. That's why I'm wearing a tie, to make me look a bit more CEO-ish. But I think today, the blood flow to the brain is more important. So I'd like to start off by talking about some numbers. First of all, this one. This is the estimated cost to the US economy per year of software errors, estimated in 2002 in a congressional report, so it's a figure that carries some weight. And that's a lot of money. That's $200 for every man, woman and child in the US. It's clear that there's a problem. I like this number. It's got shock value. I recommend it for grant applications. But today, I'd like to put it in context. This is the estimated size of the US software industry. Now, of course, a part of that is profit. A part of that is spent on sales and marketing. But I'm going to assume that a substantial chunk of that is spent on developing the software that Americans and the rest of the world uses. That's the estimated percentage of the cost of each software project that is spent on testing. Once again, this is a very rough figure. You'll see everything from 30 to 80%, but more or less of this order. So from these numbers, and granted that I'm doing a very, very rough back-of-the-envelope calculation here, I would say that the money spent on testing is roughly comparable to the cost that the residual errors impose on society. And that shows that we certainly have a problem, but the problem is as much the cost of testing as it is the costs that those residual errors impose. And if we look for a solution to this problem, then it's no use developing methods that can reduce the cost of errors but multiply the cost of testing by a large factor, because they just won't succeed. They wouldn't be economic for society as a whole. The right way to approach this problem is to try to reduce the cost of testing. And if we can improve quality at the same time, then we have a solution that potentially can make an impact on mainstream software development. Well, okay, if we'd like to affect testing, how is it done today? Well, all too often, testing in industry is done entirely manually. People sit down and they test the code and they see whether it seems to be working. Surprisingly, many companies, naming no names, will tell you that they can't afford to test at all. They let their customers do that. But what is the state of the art? The best practice? It's to use test automation, in which you have your software under test, you have some automated test cases, and these are little fragments of code that invoke the software and then check that the results the software produces look correct in this particular case. These things are run on some kind of test server, which will generate a report showing which tests failed. And most commonly, this test server will be run every night, so that if you screw up during the day, then with luck, you'll have a bug report on your desk in the morning showing which tests the system now failed. And to make this work even better, then what people do is every time a bug is found in the system, they will add a test to the automated test suite, so that that mistake can never be made again. Or they'll add a test that reveals the bug that's just been found. Okay, so just to be concrete about this, let's take an example. I'm taking the Ericsson AXD301. It's an ATM switch. That is the kind of switch that forms the backbone of a telephone network nowadays. And Ericsson developed one of those a few years ago. It's controlled by 1.5 million lines of Erlang code. And it's tested, well, that Erlang code is tested by 700,000 lines of Erlang test cases. And this proportion is pretty standard within Ericsson. 35% of the code that is written within Ericsson is test cases. So we can see from that that these automated tests are an enormous quantity of code. That makes them costly to write. It makes them costly to maintain. If you change an interface in the software, then a large number of test cases may need to be changed before the test suite will pass again. People will tell you, but that should never happen. Interfaces shouldn't change. They'll tell you the next day how much time they spent the previous week fixing test suites because an interface changed. So this is costly to maintain. Also, the automated test cases are, generally speaking, not very good code. People don't put a lot of software engineering effort into their test suites. So there's a lot of cut and paste code in there. And that makes it particularly awkward to maintain. What's worse, this is the percentage of errors that automated testing actually finds. That is, 85% of errors are found the first time a test is run. Only this last 15% are found by repeating a test. And that's not so surprising, really, is it? I mean, if you don't change your software at all during a day, and the tests pass the night before, then they'll pass the following night also. The fact that you run more tests doesn't give you any greater certainty that the system really works. So this kind of automated testing is certainly helpful. People will say, it may only catch 15% of errors, but this is the most embarrassing 15%, because your customers often have already reported them to you. But it's not a complete solution to the testing problem. Okay, so the question is, can we do better? Well, let's look at the structure of automated test cases in a little more detail. Typically, each test case can be broken down into two parts. It will contain some test data, which essentially specifies which test case we're going to run. And then there'll be some assertions that judge whether or not this particular test has succeeded. Often an assertion will contain expected results from the system and simply check that the actual result is equal to the expected result. So our proposal is to replace thousands of test data by a test case generator, which can, in principle, generate any of these automated test cases, and potentially many more. When we do that, of course, we also have to replace the assertions. We can't work with assertions that judge the correctness of a single test. We have to replace them by some kind of test oracle, which decides whether or not any of these possible tests has succeeded. So in principle, by taking this approach, then we can replace enormous volumes of code for automated tests by a compact test case generator and a compact test oracle. So in principle, we should be able to get away with very much less testing code. At the same time, if the test case generator is random, then we can hope to generate more and more unique tests the longer we test. In other words, every night that you rerun automated testing with such a method, there's a chance that you'll run some tests that have never been run before and find some errors that have never been run before. And so over time, you can hope that the system that you're testing will become more and more reliable as more and more of the errors in it are found. So this approach is built into a tool called QuickCheck, which our little company is selling. Many of you will be familiar with the Haskell implementation of QuickCheck. We're selling a re-implementation and extension developed in Erlang. For those of you who aren't familiar with it, I have an example of a QuickCheck property here, a QuickCheck specification. QuickCheck tests software against general properties, such as this one. Now, I realise this is Erlang and the syntax will be unfamiliar to many of you, but it's not that hard to read. Question mark introduces a macro, but you can read for all just as a universal quantifier. The first argument is a pattern. Curly brackets are Erlang's tuple brackets, so here the pattern is a pair of x's and y's. Capital letters start variables, as in Prolog. Lowercase letters start constants and functions. So this says for all pairs x's and y's, which are lists of integers, then the usual relationship between reverse and append holds. So that's how we write properties. And having done so, then QuickCheck can test such a property by using this part to generate test data and this part of the test oracle.
You do mean that, do you?
Of course I do. Let's see what happens when we test it. Okay, so we tested the airline shell, we invoked QuickCheck, we passed the properties and argument, and oh, good Lord, it failed. Richard, do you know something? So my property failed. Actually, 10 tests succeeded, or 9 tests succeeded, the 10th failed, and when a test fails, then the test data that caused the failure is printed. So the test data was a pair of lists. In this case, if X is a list containing 2, and Y is a list of 3 and 2, then we know that the property now fails. Having done so, QuickCheck does something rather interesting. It goes on to automatically simplify the test case that has been found. We call this shrinking. In this case, after 4 shrinking steps, we end up with a smaller and simpler counterexample to the property. X's can be the list just containing 0, and Y's the list containing 1. And this is already enough to demonstrate that the property is not true. So this is the way that QuickCheck works, in brief. We start off with a specification. We use that to generate test cases. We generate lots of them, we execute them, we get test outcomes. When the test fails, then we start a search to simply simplify the test case that has been found, and we'll end up with a minimal counterexample. For example, this pair of lists that we've just seen. Now, this addition of shrinking to QuickCheck isn't in the version of QuickCheck that comes with the Haskell library, but it's a very, very important extension. And to explain why, I've just drawn this graph. When we generate random test cases, especially larger test cases than pairs of lists, then there's an awful lot of noise in them. And that's generally true of random data. So usually we'll generate a failing case which contains reams of nonsense. Somewhere in all that noise, there will be a small feature that causes the test to fail. And we can think of that as the signal. If we present the original random test case to the user, then usually the user will not be able to diagnose what the problem was. But when it's shrunk to a minimal failing case, then it's often very obvious what the problem is. So this simplification process really automates not only finding a failing test case, but the first stage of diagnosing the failure. And this is the wow factor that customers really appreciate. So, when I wrote the property up, of course, I wrote up the standard property relating reverse of the pen, and we've proved it many times, so we would have expected it to pass, really. But we know that it fails, and what's more, we know that this is a minimal failing case. And that gives us a lot of information. We know, for example, that if either list was empty, then the test would pass. Because if the test failed for an empty list, then QuickCheck would have shrunk the minimal case further. We know that 2 lists must contain different elements, because if that one could be shrunk to 0 and still be a counterexample, then QuickCheck would have done so. So we need 2 lists with at least 1 element, and probably they must be different. Let's look back at the property. Oh look, I screwed up. I forgot to swap X's and Y's in the right-hand side. And sure enough, to find a counterexample of that, X's and Y's have to be non-empty, and of course they have to be different. So I want to show you a demo, because it's great fun using QuickCheck if you haven't done so. The demo I'm going to show you is on a very small piece of code that came from a French company that does SMS encoding. An SMS, it's what we call it in Sweden, it's called a text message also. So when you send text messages between your phones, then you're using this encoding. Now you may not have thought about this, but the characters in the text message are only 7-bit characters. But they're sent in packets made up of 8-bit bytes. So there's an opportunity to save 1 bit per character by packing the 7-bit characters into 8-bit bytes. And the SMS transmission standard specifies that you should do that. Okay, well, as you can imagine, now, it's still inside. It's not going to be so good for the demo, is it? Let me just... Okay. What more... Oh, look at that. What more perfect introduction could I have to a talk on software errors? Here we are. Oh no! Oh. What happened here? Did we just wait?
5 seconds. Did you try to change your resolution? 5 seconds thing.
I wouldn't be able to read them on the phone.
Okay. Hang on. Let me adjust the resolution of the screen. Oh, that's a problem. Okay, that looks better. So here we have an implementation of packing and unpacking. It's written in Erlang. It's nicer than it might be actually, thanks to Erlang's binary syntax. So as you can see here, to pack 2 characters, we take 1 bit from B, 7 bits from A, 2 bits of 0, and then B bit shift right by 1 and so on. Anyway, there's quite a lot of code here, but it had actually been through and passed a conventional test suite at the time that we got hold of it. However, it's very easy to write a QuickCheck property that says a lot about how this code should behave. Here we are, for all messages, which will be lists of values in the range 0 to 127. If we pack and unpack the message, we should end up with the same result. Let's see what happens when we test that. We'll go to Erlang here, compile the SMS encoding, and let's quick check it. Yeah, seems to pass. Good. Let's just up the number of tests a bit. What should we take? 10,000? Oh, now it failed. There we are. If we look at the failing case, we can see that we've got a string of a number of characters, 8 characters in fact here, and it shrunk down to a list of 8 zeros. Now what we can see from that, because we know this test case is minimal, is that we can't remove any one of those characters without making the test pass. So it's got to be at least 8 characters long. And we can guess that the actual values of the characters aren't significant, because all except the last one shrunk down to 0. Okay. We can go on to generate more failing test cases. Oh look, we seem to be hitting similar ones the whole time. We can now use QuickCheck to investigate how the code is actually behaving. So maybe we think that if the length is not 8, then test should pass. Okay, so let me just reformulate the property. Switch back to Erlang, recompile, retest. Oh, there we are. Seems to work, except for, oh no, look, it's failed again. We found another failure. What can we see here? Well, that's actually 16 characters long. So maybe we might guess now that it's something to do with being a multiple of 8 characters. Let's investigate the bug a bit more closely. Let me replace this by true. Let's concentrate on the failing case. And let's test lists of 8 characters and see whether we can observe anything in common that the, ignore that the failing tests satisfy. Okay, well there's a failing test like the one we've seen before. It's testing very quickly now. We can see that some lists of 8 characters pass, but quite many fail. Do we see anything in common between the failing cases? Look at the tests before shrinking now. They've all got a 0 at the end. Is that critical, I wonder? What if I go back here and I say that if list's last of message is not equal to 0, then I think the property should hold. Recompile. Okay, 10,000 tests. 20,000. 30,000. Looks as though it might be true. So you can see that by using QuickCheck to investigate properties of the code, I've derived a lot of information about where the bug is without even looking at the source code. And that can ease the process of debugging very considerably. Okay. However, unfortunately, our industrial customers don't want to test the reverse function, or normally code as simple as pack and unpack. Rather, they want to test things with side effects. And their test cases are more likely to look something like this. This isn't an industrial one, but you might find it in something like this in an industrial test suite. This is a test case for the Erlang process registry, which is a kind of local name server. And if we go through it, what we're going to do is we're going to test registering a process under a name. So first of all, we've got to create the test data by spawning a process that we can register. Then we can actually register it. Name is an atom here, that's the name that I'm using. But that has a side effect. It doesn't deliver a result we can inspect. That's the operation we want to test, but now we need to perform further operations to try and see whether or not register behaved correctly. So we can look up the name now. That will return another PID. And now those two PIDs should be the same. So we can write that assertion in the test case. And then finally, because typically we'll be running many thousands of automated tests, we have to clean up after each one and leave the registry in the same state so that the next test case can run. And that's what the last unregister is doing. Okay, so this is more the way that industrial test cases look. We've got a sequence of calls to some API, and we've got a number of checks that the results from the API correspond to expectations. How should I formulate this as a QuickCheck property? What should we generate? What is the test data? What is the assertion? Well, actually, there is a very easy answer to those questions. And that is to see that what we need to do is to generate test cases that are programs. That is, a test case is just a short program making calls to these APIs. And then we execute the tests just by executing those little programs. We'll get a test outcome. And now QuickCheck can work in exactly the same way. When a test fails, then we can start simplifying these programs and end up with a minimal program that provokes a fault. So we can use exactly the same method, but the test data must now be programs, a symbolic representation of programs. And it's very important that we use a symbolic representation here, and that we don't just randomly run a test. We've got to have a symbolic representation of it, so that we can print it out to the user, and above all, so that we can simplify it. And as I said before, that's where the power of the tool lies. Okay. What have I got? Okay. So we've built a library on top of the basic QuickCheck mechanism to support this kind of testing. And that's necessary because providing QuickCheck as you've seen it so far for this kind of testing will be like saying, you want to prove imperative programs correct? Here's predicate logic. Of course, we need to build more on top of that to make it practicable to do this kind of testing. And what we do is we model the system under test by a state machine. So if we take the process registry again, to model the state of the test case, we need to keep track of which processes have been spawned, which are available for registering. So we'll represent the state by a record containing a list of PIDs, process identifiers. And we'll also need to keep track of which registrations have been performed, so what we expect the registry to contain. And we can model that by a list of pairs of atoms and process identifiers. And our customers define such a state, and then they define a next state function that specifies how each operation that can appear in test cases affects this state. So for a simple example, let's imagine that I define such a function for 3 operations: spawning a process, registering it, and unregistering it. And I won't show you the definition, but what spawn does is it adds a spawned PID to this list of PIDs, register adds a pair to the list of registered names, and unregister removes such a pair. As soon as I've defined those state transition functions, then I can start running tests. The specification isn't complete, but I can test it. And if I do so, then I haven't specified any assertions to check yet, so the test will fail only if an exception is raised. Well, an exception is raised. Typically, I'll start off with a long failing test case with many operations in it, but it'll shrink down to this. This is what the user sees. It's a list of commands represented by Erlang terms that are just the abstract syntax for a little program. So you can see the abstract syntax here is some kind of binding called set, setting a variable, and abstract syntax for function call to unregister with this list of arguments. So this represents, this little test program, unregister A and bind the result to V1. That raises an exception. Why? Well, obviously, because I'm trying to unregister A, and I haven't registered anything. So there are various ways I might deal with that. One thing I might say is that test cases ought not to contain calls of unregister that try to unregister something that hasn't previously been registered. And I can express that by specifying a precondition for the unregister function. Here is the code that our user would write. We specify that a precondition for this call in this state S is just that the name occurs as a member, okay, in the first component of a tuple in that regs component of the state. So that's just testing that we know we have previously registered that name. If I add that precondition, then QuickCheck will no longer generate test cases of this sort, and so we avoid that exception. So we can test again. Bang! It fails. It fails with another counterexample, and once again, this is a counterexample extracted from a much larger list of commands. We can read it, see what it does. We're spawning a new process, binding its identifier to variable 6. Then we're calling register to register variable 6 under the name A, and then we're doing the same thing again. So here is the same program expressed in an easier to read syntax. And of course, what we're seeing here is a very similar problem. I'm trying to register a second process with the same name. And actually, the documentation tells us that we mustn't reuse a name, neither may we reuse a pig. So this second call raises an exception for two different reasons, in fact. And of course, I could now add another precondition to rule out this kind of test. Or maybe I want a test that register raises an exception precisely when it should. Well, in that case, I could fix the problem by a different method. I could add a post condition to register. In this case, our user would write this code, which says that if we start in this state S, we perform this call, and we receive the result V, then the result V should either be true, indicating it's a success, or it should be an exceptional value, tested for by isExit. And so I simply test whether I expected this call of register to be okay. If so, I check that the actual system returned true, and if not, it returned ifexit. So now I'm doing what's called negative testing. And I can run the tests again, and we get another counterexample. Okay, so this one's a bit trickier. Remember that this is a minimal counterexample illustrating the problem. What are we doing? We're spawning a process and binding it to variable 2. We're registering it first under the name A, then under the name B. I'm allowing that, remember, but I'm expecting it to fail. We're spawning a second process and we're registering that under the name B. And something went wrong. Our spec and our code were inconsistent. Well, that can only be because of the success or failure of the calls to register. So what's gone wrong in this example? Well, the spec says the first call to register should succeed. And it did. The spec says the second call should fail, because we're reusing the same process identifier. And it did. So that's all right. But the spec says that the third call to register should also fail, but it succeeded. So that's the problem. And why did spec say that the third call should fail? Because we were registering the name B that we previously registered. But the code obviously considers that we didn't previously register B at this point, presumably because this call raised an exception. So what's the problem here? Well, the problem is that the spec that I wrote defined the next state function for register to say that it makes this association between the name and the pig. And my next state function ignores the fact that register might raise an exception. If we look at the documentation that I wrote my spec from, it says register associates the name with a PID. It doesn't say, provided no exception is raised. But of course, that is actually the case. Now, you might think this is a natural interpretation of the documentation, which I suppose it is, but the documentation does not actually say that registration does not happen if an exception is raised. And when we write a QuickCheck specification, then we have to be precise. Okay. I want to show you some examples of real errors that we found in industrial code by using this kind of testing. The first one comes from a media proxy. So what this is it's a box that forms part of a system for carrying multimedia telephony over the internet. And a media proxy has as its purpose to connect calls across a firewall. And it's controlled by an external controller that tells it to set up and take down calls. It does so by adding and removing callers to a call. Now the protocol that's used can support conference calls with any number of callers, but the media proxy is restricted to only 2. So here's a test case that we found. We add the first caller to a call, we add a second. Well, now the call is full because it contains 2 callers, so we can't add a third, but we can, of course, remove a caller. Now it's not full, so we can add a third. It's full, but we can remove one of them. Now it's not full. We can add a fourth, and we can remove one of them. And when we removed that fourth caller, then something inside the proxy crashed. So, I love this error for many reasons. One reason is that we obtained it by simplifying a sequence of 160 commands. You can imagine, if we presented that 160 command sequence to the user, nobody would have been able to figure out what the problem was. This sequence of 7 commands is short enough that you can reasonably hope to track down the error. I also like it because this is a test that nobody in their right minds would do manually. It looks really silly. I mean, if we've added and subtracted a caller once, twice, well, by induction it works 3 and all further times. Only it doesn't. And it's not just that testers reasoned by faulty induction. It's also that, in fact, there were more operations that could appear in test cases. And you cannot reasonably test all sequences of 7 operations. It's just not practical. There are too many of them. And building each one of these tests manually involves constructing complex protocol messages with many parameters at each stage. It's not possible. The other reason I like this error is that although it looks like something that would never happen in practice, the problem turned out to be that the first time a caller was subtracted, every time a caller was subtracted from a call, internal data structures were corrupted. It just so happened that if all you did after that was subtract the other caller, then nothing actually crashed. But we all know it's not good to have corrupt data in your system. Next year, somebody could have modified the code, trusting that this system that's been working perfectly for a long time actually contained the data it was supposed to contain. Their code would then have crashed because of this error. So this bug was well worth finding and correcting. Here's another error that we found recently. This is in a 3G radio base station. Those of you who have 3G phones, they may be connected at this very moment to one of these things. So such a base station opens radio channels to all of the handsets that are currently making calls. But the handsets that aren't making a call, they don't have a dedicated radio channel to them. Instead, there's a single signaling channel that is used to communicate with passive handsets, to start calls, this kind of thing. Now notice I said a single signaling channel, so there should be only one of these. Nevertheless, they are configured when you set the base station up. So you send a setup message, and the base station responds saying, yes, I've set up my signaling channel. And if you send another setup message, then of course that should be rejected. But what we found was that if you pick just the right parameters, just the right frequencies and so on, in these 2 setup messages, it was actually possible to get a second setup accepted. Once you've done that, all bets are off. You violated a fundamental invariant of the implementation of the base station. And sure enough, after a few more commands, the base station became completely unresponsive. So when we tried to debug this, then we got a surprise. Although we knew that the base station was implemented using C++ and Rose real-time, what we found in the log was Java exceptions. That puzzled us for a while. But it turns out that the base station has an operator interface, and that interface has a GUI. The GUI is programmed in Java. And while the C++ code didn't notice immediately that its invariants had been violated, the poor operator interface that was trying to display the state of the base station just fell over in a heap at once. And so that was the quickest way to detect that something had gone badly wrong. Here's another example that we've done recently together with a couple of other companies, testing Symbian mobile phone handsets. So in this case, we have a laptop that talks over Bluetooth to the two handsets and tells them to perform various phone-like operations. One of the things you can do is you can tell the first phone to call the second one. The second one then starts ringing. And at this point, there's a number of things you can do. You can accept the call, you can reject the call, or you can just wait. If you wait, eventually this first phone will time out. And now, for long timeout periods, everything's fine. But if you time out a bit too quickly, then that phone crashes. So we had somebody working on this. When mobile phones are tested, then they're given to guinea pigs who use them, and typically every couple of weeks, the guinea pig will manage to crash the phone. So our guy was crashing these things 15 times a day. It was quite easy to find sequences that would stop the things from operating. The most awkward problem was that at this point, if you want to run the next test, you have to remove the battery and put it back in again. So test automation has its limits for these things. Okay, I will skip a few slides on testing concurrent algorithms. And come down to the bottom line. So we're trying to make a business of this, and of course all that matters to our customers is, will they save money? What is the return on investment? It's very difficult to demonstrate that you will save customers money. I mean, we may think that testing against formal specifications is really cool, and it's bound to be a good idea, but that doesn't convince people with budgets. So we've spent a long time having great fun working with our customers, but it's taken maybe a year to get to the point where we now have customers who are prepared to say that this is saving them money. So within Ericsson, there's been a study that was recently completed that looked at some of the errors that have proven costly in the past. So what we can see is that QuickCheck can find errors that cannot reasonably be found by manual testing. The example I showed you with the media proxy was one such case. It's simply not practical to write enough tests to cover all of the kinds of failure that QuickCheck has been finding. Those failures do, however, crop up in practice. And when they crop up in practice, they can prove very expensive. So the results that appear in a master's thesis now show that QuickCheck can save a factor of 2 and 4 on the cost of such expensive errors. So we're very happy about this because now we actually have a customer who is prepared to tell other people that we can achieve savings of this magnitude. And for a little company, that's a big step forward. Okay, so you're probably wondering lots of things at the moment. For example, why are we building a testing tool in airline when the airline market is tiny? Why aren't we building a testing tool in C++ or Java or C#, the language in which the systems that customers write are written? Well, of course, there are some kinds of testing for which it's vital that test cases are written in the same language as the code under test. When you're doing unit testing and you want to put tests in the same module as the code under test, of course it has to be in the same language. But what language are the systems that we're testing written in? The base station I mentioned was using C++, generated from Rhodes real-time, Java. There is no single language in which the systems are written. And so this question doesn't really make sense. And in fact, the telecoms market is a very nice market for using a different testing language, because the products tend to be rather isolated black boxes that talk to other products using standardized protocols. For example, the media proxy, a media gateway, is controlled by a media gateway controller talking the megacode protocol. The radio base station is controlled by a radio network controller talking the NBAP protocol. And all of these protocols, there are hundreds of them, are standardized by international telecoms bodies. Why? Because customers like this. It means that, in principle, they can buy a radio base station from Ericsson and a radio network controller from Siemens, and they should work. I'm not sure they would, but that at least is the idea. For us, it means that these systems have well-defined standardized protocols that can be used for testing. And that in turn means that the language in which tests are developed by no means has to be the same language that the system is implemented using. In fact, it often isn't. There's a language called TTCN3, which is somewhat popular in the telecoms world, and its only purpose is for writing tests. Here's a little fragment of it. You can see it's sending messages and receiving messages, and look, here's an alt. These are Dijkstra guarded choices. It's a bit like Occam, or indeed a bit like Erlang, in fact. And people are prepared to contemplate writing their tests in this sort of language. So why not write them in Erlang? In fact, Erlang is being used just as a test scripting language within Ericsson by groups who are not developing systems in Erlang. That might surprise you, but it's for quite simple reasons. One reason, believe it or not, is pattern matching. Here's a little bit of Erlang code which calls insert and matches the result against true. Here's another line which calls insert again, catches an exception and matches that against an expected form. Pattern matching makes it very easy to check that a test has returned the value that you expect. And that makes Erlang attractive for test scripting. Something else. Erlang comes with a test server called Common Test, which is rather nice. And that generates HTML reports that you can click through, see how many tests passed, how many tests failed, organizes running the tests, does all of that stuff for you. And believe it or not, you can have more success saying to people, we've got this great test server, wouldn't you like to use it? By the way, you'll have to learn its scripting language. People are readier to accept that at times than, why don't you try this functional programming language Erlang? So Common Test is really quite a big factor in spreading Erlang as a test scripting language, but it's perfect for us. Okay, you've seen we're building state machine models of software and we're using those for testing. So wouldn't it be more sensible to use, for example, UML that can describe state machine models of software and test? And then we could draw state diagrams looking something like this. Here's a state diagram for the media proxy. I start a call, I can add a caller, then it's half full. I can add another, then the call is full, subtract one, go around this loop, subtract the last one, and I finish the test. And there are model-based testing tools, many of them, which will take this kind of diagram and generate a collection of tests that visit every state, for example, or that traverse every transition. But the test we found that crashed the proxy traversed this loop 3 times. If we think of the test we found that crashed the base station, well, the important thing wasn't that we tested sending 2 setup messages. It was that we tested sending 2 setup messages with the right combinations of parameters. So that I don't have a great deal of confidence in taking such diagrams as a starting point for testing. This kind of state diagram is an abstraction of the real state of the system, and that abstraction may very well mean that you miss just those cases that will lead the system to fail. Okay, well, what about functional programming? What has the work that we're doing to do with functional programming? Well, the answer is a lot. For example, here's code I showed you earlier, the post condition for register. Look, it's taking the state before the call to register as one parameter, and the result from the call as the other. So I need to simultaneously have available the result of the call and the state beforehand. Well, in a functional language, there's absolutely no problem with that. But imagine if I wrote my specifications in an imperative form, so that just running the specification of register to derive its result destroyed the state beforehand. How would I write the postcondition? Functional programming is very natural, I think, for specifications, even of systems that are not built with functional languages. Here's something else. Our customers write this code. Look, they're pattern matching on a call to register. They're doing symbolic programming. Of course, we need a language that makes that easy. Something else you may wonder is, you've seen that when I test this, then the test case that's found starts shrinking. Where is that specified? Well, there's only one place it can be specified. It's in these generators here. What we're using is a classic domain-specific embedded language with a very rich semantics that includes how to generate test data, how to shrink it, and most recently, how to inject faults into test data. That's turned out to be quite important. And all of that is captured in a compositional way that means that the user doesn't have to think about it, except in those cases where some shrinking is being specified or some fault injection is being specified. So we're taking advantage of all the techniques of functional programming that we know and love in order to make this work smoothly. Skip that. I want to show you something else. Here's how you might attempt to generate a positive integer using QuickCheck. Here we are. This is an integer generator. Bind it to n, return the absolute value. Doesn't work. It doesn't work because n there is bound to a generator, an abstract data type, and you can't pass that to absolute value. Here's what you really have to write. Let is a macro, but just read it as, let n be the value bound to an integer, and return the absolute value of n. So this is what I use as write. It would look a little more familiar if I were to write it like that. So QuickCheck is based on a monad. We're using a monad in Erlang, even though Erlang has effects, because, well, it's not the same monad. And we couldn't make the experience of writing test case generators anything like as smooth without the concept of the monad. So thank you, Eugenio. Thank you, Phil. Your work is making our company possible. Why aren't we using Haskell? Well, one is we had a customer who wanted to use Erlang. And I cannot overemphasize the importance of that for a company. But actually, the choice of Erlang has turned out rather well. And the reason is, we don't have that pesky type system to get in our way. Look at this. Our customers write this code. They're pattern matching on a data structure representing a function call. Here's a list of arguments. Give you a clue, they have different types. Our customers write this code. They don't have to define a data type to represent the function calls appearing in their specification. They don't have to write an interpreter for that data type. An awful lot of code is generic and is provided by us. And they just write this down. This is already difficult enough to try and persuade non-functional programmers that they can do. Here's another example. This is an Erlang generator for times of day. See, curly brackets form a pair. Choose an hour from 0 to 23. Choose a minute from 0 to 59. Here's the Haskell version. So the two calls of choose return generators. Here I have a pair of generators. I need a generator for pairs. Of course, we need a function to convert the type. That's what lift m2 comment is doing. But on the Erlang side, well, we just interpret a generator embedded in the data structure as a generator for data structures. Now, you may prefer either one or the other of these, but I can tell you which one is easier to sell. Not only that, but this problem isn't confined to generating pairs. It appears again in larger and larger examples. This could be a large protocol message, in one field of which we embed a generator. doing the same thing in Haskell. We couldn't even write down a protocol message with a generator in one field. It would be a type error. So, our goal here is to help develop software with fewer errors. So, why bother with all this stuff? Why not just build systems with functional programming in the first place? I'm sure we all think that would be a better idea. But it's a very tough sell. Persuading a company that they should change all of their implementation technology and build their products with a functional language instead is a very big job. Some companies are doing it, Ericsson and parts of Ericsson among them, but it's a tough sell. Persuading a company to adopt a new test tool with a new test scripting language is a much, much easier sell. And we've seen now, actually, we have allies in this process. Functional programming has become something that isn't just for pointy-headed academics, it's for the cool dudes. And some of those cool dudes have come to us. They're interested in introducing QuickCheck into their companies as a way to do some functional programming. So I think there's a chance that QuickCheck can help spread functional programming into more and more companies. And I certainly hope that's the case, because we're betting on it. Thank you.
Plenty of time for John to answer some questions.
So the arguments that you gave for using Erlang, the ones that were up there, would apply equally well to Scheme. Is that the case?
Yes.
John, can you repeat the question for people?
The question was whether Scheme wouldn't do just as well as Erlang. And the reasons that I gave about the Pesky type system, those certainly would apply equally well to Scheme. We have a customer for Erlang. We don't have a customer for Scheme. That's a big difference. Also, I think, in the telecom sector, which has turned out to be a fruitful sector for applying this kind of technology, then Erlang comes with a whole environment of tools for connecting to different kinds of telecom systems. You know, you want an ASN1 compiler, you can just take one off the shelf. I don't know whether Scheme is as well suited to this particular application domain. That makes a big difference in how easy it is to set up tests. Richard?
How do you define the shrinking relationship when the expression of programs? I don't see.
Well, there are various things you can do. An obvious thing is the programs are very simple. They're straight line programs. They're lists of function calls. You can simply omit some of the function calls. Now, you have to be careful that you respect the semantics of the programs when you do that. So, for example, you don't want to end up with unbound variables. You don't want to end up calling functions whose preconditions are no longer satisfied. Nevertheless, it's possible to simplify test cases by deleting commands. That's the most important thing we can do. The other thing that we can do is these commands have large arguments. You haven't seen them in this talk, but the arguments can fill several screenfuls. And those are protocol messages that the commands are going to send. They contain many fields. We can shrink those fields. And it's very useful to see the result of doing so, because typically fields that shrink to their minimum values are not responsible for the test failure. Likewise, there are optional fields in these protocol messages. Well, we delete those during shrinking. So that if you know what the minimum values of the fields are, and you compare the actual protocol sent with the minimal values, then you can often see, aha, it must be this field that is responsible for this test failure. So there's a lot you can do, in other words.
But you can't prove the result is actually minimal in some sense. It's just simpler.
It's minimal in the sense that QuickCheck's shrinking strategy will not reduce it. So, when we shrink, then in principle we're shrinking in some kind of ordering, and the final failing test should be minimal in that ordering. But the shrinking strategies can be specified by the user. You know, we don't know what the user will do. They could do any kind of stupid thing. And if they do, then we can't give any guarantees. Joe?
How does this fit in with test-driven development? Would you recommend I mean, here I get to we're bolting on test cases after you've done the development. Would you recommend a new way of working where we write the test cases into the testing, or the development?
Absolutely. So I like to call it property-driven development. And what I do myself is when I write code, I start off by writing down properties that the code should satisfy. And as soon as I've written code, I can run QuickCheck and test them. And it is a rather amazing experience. You write some code, you test it, and it goes, BAM! It doesn't work. Here's a failure case. And you get a very short example that demonstrates that you missed something. So you fix that, and you test it again. BAM! It fails again. Here's another failure case. You go through a few iterations of that, and this doesn't take long. And then 100 tests succeed. And that's a weird moment. What do you do next? Well, I usually hit up arrow return, and I run another 100 tests. And then I think, okay, how about 10,000? That doesn't take very long either. And then, you don't know what to do next. It feels as though there's something missing. And there is something missing. What's missing is all the time that you normally have to spend thinking up new test cases to try out the code. But, you're done. You just have to go on to the next bit of code and write some properties for that. It's a very attractive way to develop programs. I like it very much.
GUIs and web interfaces are often hard to test. Do you have an approach there?
GUIs and web interfaces are often hard to test. Do we have an approach there? We don't have any specific approach for testing GUIs, for example. The trouble with a GUI is that an error may be revealed only by something you see on the screen. And of course, we have to be able to observe errors programmatically. We encountered that with testing these mobile phone handsets, where sometimes something would crash inside the phone, and the only way to discover that was that it displayed a blue screen to the user. So the guy who was doing this actually added something at the end of his test cases that captured the screen image, sent it back to the laptop where it was analysed to see, does this look like a crash screen? If so, the test has probably failed. So that's the kind of thing, the kind of hoops we have to jump through to do that kind of testing. Web interfaces may be easier because if you're testing some kind of web service, then you've got a clean programmatic interface to it. So the same problem doesn't arise.
One more, I think.
Torsten.
QuickCheck for high school is free, right?
Yes.
QuickCheck for airline, which has the extra shrinking feature, costs lots of money. Is this a bit of a problem?
Doesn't seem to be. So I'm not expecting to sell lots of copies of this version of QuickCheck to Haskell users. But the rest of the market is plenty big enough. And what we're supplying is not just software with a license, but we're supplying, for example, this state machine testing library. There's quite a lot of clever stuff in there, and it dramatically simplifies testing side effects in code. We're supplying training, we're supplying consultancy. There's a whole package. Most of it just isn't available with Haskell QuickCheck. So we haven't found that Haskell QuickCheck is a competitor that people bring up. Rather, they'll bring up model-based testing tools as a possible competitor. I'm much more worried about those.
We've cut a little bit into our break, but I'd like to remind you that we're on a 25-minute schedule, so the next session begins at 10:25, and perhaps we can end by thanking John one more time.